In this episode, we're going to break down how a marine propulsion system actually works, not just mechanically, but from an automation, electrical and control system perspective. We'll look at the propulsion control system, the power management interaction, hydraulic actuation behavior, and instrumentation feedback, and why integration between these layers determines propulsion reliability. A marine propulsion system converts prime mover energy into thrust to move the vessel. In diesel mechanical propulsion, this includes main engine, reduction gearbox, shaft line, fixed or controllable pitch propeller. In diesel-electric propulsion, engine power is converted to electrical energy, distributed through the main switchboard, and supplied to propulsion motors. However, beyond the mechanical layer, propulsion stability is governed by a propulsion control architecture that regulates torque demand, speed control, and load response under transient conditions. When a throttle command is issued from the bridge, the control sequence follows: Bridge Control Unit PLC or DCS Governor Module Fuel Indexing Torque Output RPM Feedback. This closed-loop control relies on stable PLC scan cycle timing, proper PID tuning, reliable communication protocols, clean analog feedback signals. If scan cycle time increases from 15 milliseconds to 70 or 80 milliseconds due to aging hardware or added logic complexity, governor response may lag during rapid load demand. This results in temporary frequency dips, torque oscillation, and increased generator stress. Common minute issues include increased PLC scan cycle time due to expanded logic, PID tuning drift after software updates, CAN bus or Modbus communication jitter, governor actuator backlash, fuel rack hysteresis, delayed RPM feedback filtering. Even small PID gain imbalance can cause torque oscillation, governor hunting, frequency instability under maneuvering load. These deviations may not trigger alarms immediately, but they reduce propulsion stability margins. In integrated power vessels, propulsion demand directly affects generator performance. The power management system controls generator load sharing, kilowatts or kilovoltamps reactive balance, frequency regulation, under-frequency and overload protection, automatic load shedding. When propulsion load increases rapidly, generator load rises proportionally. If droop settings are mismatched, AVR response is slow, or protection thresholds are overly conservative, the PMS may initiate protective action before the system stabilizes. Minute electrical issues include mismatched droop characteristics between generators, uneven kilowatts or kilovoltamps reactive sharing, slow AVR excitation response, protection relay miscalibration, oversensitive under-frequency threshold, improper load ramp rate settings. During rapid torque increase, generator load spikes. If protection reacts faster than governor stabilization, propulsion may momentarily drop power. For fleet operators, this translates to propulsion instability, unnecessary trips, and reduced operational confidence. In controllable pitch propeller systems, hydraulic actuation defines thrust behavior. The pitch control system consists of hydraulic pumps, servo valves, actuators, position feedback transmitters, gradual hydraulic pressure decay, servo valve contamination, or air ingress into pneumatic lines can introduce response lag in pitch adjustment. Common degradation issues: servo valve contamination at micron level, internal leakage in hydraulic cylinders, pressure relief valve drift, accumulator precharge loss, slow pitch feedback potentiometer response, air microbubbles in pneumatic assist lines. Even a slight delay in blade angle correction can create torque mismatch, causing governor hunting and unstable load sharing. These are degradation behaviors, not sudden failures. Propulsion control depends entirely on accurate feedback signals. Critical inputs include engine RPM, torque measurement, hydraulic pressure, temperature monitoring, signal drift and torque sensors, incorrect scaling in transmitters, grounding faults in 4 to 20 mA loops, or calibration deviations can alter control decisions. Minute but critical signal issues include 4 to 20 mA loop grounding interference, shield termination errors, Sensor zero drift after temperature cycling. Torque transducer calibration offset. Noise and magnetic RPM pickup. Improper signal filtering in PLC logic. The control system behaves exactly as but it responds to the data it receives. When control latency, PMS sensitivity, hydraulic lag and signal drift combine, the propulsion system loses stability margin. This does not always cause blackout, but it reduces load handling capacity, fuel efficiency, component lifespan, operational confidence. For chief engineers, this requires periodic control loop review, PMS coordination audit, hydraulic performance testing and signal integrity validation. For fleet directors, system integration integrity directly influences lifecycle cost and risk exposure. At SMEC, we support end-to-end vessel engineering, including propulsion control design, PMS integration, electrical panel upgrades, hydraulic optimization and full system behavior audits. If your vessel is experiencing load fluctuation, instability under maneuvering, or propulsion performance drift, the root cause may lie in system integration. We also offer structured training programs for students and working professionals in automation, instrumentation, electrical systems and emerging technologies, building future-ready technical capability.